Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic we're going to discuss optimizing a function of a vector variable. So in this topic, we're going to be describing what's covered in this upcoming section, that is, optimizing functions of a vector variable, specifically finding maxima and minima of real-valued functions where the argument is an n-dimensional vector. So we're going to discuss how this is actually much more difficult than finding the minimum of a real valued function of a real variable, and then we will describe the three algorithms that we will be covering in this section. Now, with a differentiable function of one variable, if the function is increasing in one direction, it's of course going to be decreasing in the other. So it's not that difficult to find a local minimum. However, even if we have a function that is of a two-dimensional vector, we now have potentially infinitely many directions which we could potentially consider to find a minimum. Now, fortunately, if the function is sufficiently differentiable, we can calculate the gradient, but this may not always be possible. One nice feature of the gradient is that the gradient itself yields the direction of maximum increase. Consequently, the opposite direction of the gradient is the direction of maximum decrease. Now, suppose you're in the Scottish Highlands and it's foggy. You'd like to get home, and your home's in the valley. So how do you get there? Well, of course, if you knew exactly which direction your home is, you could simply go in that direction. But suppose you have no global information. Consequently, in this case, if you were trying to get down into the valley in the quickest way possible, given only local information, then the most reasonable approach would be to walk in the direction in which it is the steepest in a downhill manner. Now, for a sufficiently differentiable function at a minimum, the slope in every single direction is going to be 0. Now, unfortunately, a function at a point could actually be a minimum in every single variable but one, and that other point may actually cause that function at that point to actually be a saddle point as opposed to an extremum. So we are going to have to be a little bit careful as to what we declare to be an extremum. So, for example, if we just have a function of a two-dimensional vector u, then this particular function has a minimum at u equaling the 0 vector. However, both of these two functions, which are only simple modifications of the one we see above, have saddle points at the origin. So in this topic, we're going to look at algorithms that try to find local minima for functions of a vector variable. We're going to start by looking at the Hooke-Jeeves method. Now, this is a generalization of the step-by-step algorithm that we discussed before that walks towards the minimum. However, this will now do that in n dimensions. We'll then look at Newton's method for finding extrema in n dimensions. And once again, this is going to be a generalization of using Newton's method applied to the derivative to find an extremum of a function of one variable. Finally, we're going to look at the gradient descent technique. Now, this is a technique that converts a problem of finding a solution in n dimensions to a problem of finding a solution in one dimension, that is, the techniques we've already looked at. So, following this topic, you now have an overview of the ideas that we will be covering in this section. Finding extrema, specifically finding minima of functions of a vector variable. And you understand that we will be looking at 3 different algorithms for finding such minima of a real valued function of a vector variable. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!